Okay, good morning. I've just given you back your quizzes. Also, I've in the last couple of days graded some of the homework assignments that had been in the queue, so please take a look at the comments that I put on there. The solutions to your homework assignments are also available on Blackboard right now. And this last assignment I looked at a little bit more closely because I had some extra time. I think that in some cases you're going to need a little bit of extra practice on StormCAD. Now the quiz that's coming up on Friday is going to be HY8 related, but the midterm exam which we have, there will be a StormCAD problem on that. So you definitely want to close the loop, and if you didn't get the homework exactly right, then maybe work through it another time and learn how to optimize the pipe sizes and make sure that everything's entered in correctly. So please take a look at the solution that I've posted so that you're sure that you've got StormCAD nailed down. Alright, homework number 4, which is having to do with precipitation. That's due on Monday of next week. We're going to be talking about precipitation today. Today we're going to go into the theory, and then on Friday we're going to go into some calculation-based stuff having to do with precipitation. But before we get into the theory of precipitation, we're going to look very briefly at the units having to do with the rational method. Q equals CIA. I'm going to show you how it works out to cubic feet per second when you're putting in inches per hour and acres. So before we get to that illustration, are there any announcements related questions? Okay. So, Q equals CIA. What is the C value? It's a ratio, but it's not the ratio of infiltration to rainfall amount, and it's not the ratio of infiltration to runoff. It's the ratio of the runoff amount to the rainfall amount. So the stuff that's coming out of the sky, what fraction of that is going to be flowing over the surface? That's the C value. So that's why for concrete, for instance, the C value would be 0.95. That means for every inch of rain that comes out of the sky, 0.95 inches of rain will flow over the surface. And that other 0.05 inches of rain is just going to be stuck on the surface of the concrete, wetting that to provide the lubrication, so to speak, for the rest of the sheet flow. All right, so the first thing I wanted to emphasize is I don't think I'd put it as succinctly as this before. It's the runoff amount divided by the rainfall amount. So let's say that we have a parking lot with a C value of 0.9, and we know the area of the parking lot, and we know the rainfall intensity that applies. And how would we pick this rainfall intensity? In the real world, as you learned from the homework, what you'd do is you'd estimate the time of concentration, and then you'd use the applicable time of concentration off of the intensity, duration, frequency curve to figure out which rainfall intensity applies. Let's say that I already did that for you. I found the time of concentration and the applicable rainfall intensity. We just want to look at the units, because what I've told you before is that you get CFS, cubic feet per second, by multiplying inches per hour by acres. Now it's just a coincidence that that works. That's not actually a fundamental conversion. It's a coincidence. I'll show you how closely it matches with the fundamental conversion. But do part A real quick if you don't mind. If you've got your calculator, just multiply 0.9 by 6.4 and multiply that by 2.7. And what is our peak runoff in cubic feet per second? .55 CFS. Okay. So this is just the first method where we're assuming it all works out, but let's not rely on that until we've checked to make sure. And the way we can do that is, first of all, converting inches per hour into feet per hour. And so the rainfall depth of 2.7 inches per hour falling out of the sky, that's 0.225 feet per hour. And we can convert that into feet per second by dividing by 3,600. So now it's 6.25 times 10 to the minus fifth feet per second. Now the area of 6.4 acres, does anybody know off the top of their head the conversion between acres and square feet? 43,560. You got it. You should be very proud. That's one of knowing some of those random conversions is just, for some reason, I really like it. I like that I know it's 43,560. It's just okay. Good. It was burned into your memory. All right, so 6.4 acres multiplied by 43,560. So this is how many square feet the parking lot is. And so now we have some units consistency here. We've got an area that a depth per time is falling over. So if we multiply those two parameters together, we're going to get volume per time. Okay, so it's 15.7 CFS if we have the runoff coefficient, the depth per time falling over an area. So now compare those two numbers, essentially 15.6 CFS and 15.7 CFS. The thinking is that that's close enough together. That's certainly more precise than our ability to characterize the runoff coefficient, the C value. I mean, usually, unless you've calibrated an area and you kind of have done the, measured the flow rate during a certain rainstorm of a known intensity, that's a way that you could back calculate the C value. But if all we're doing is we're looking it up out of a table, our capability of accurately estimating what C value should be used is way worse than how closely this agrees. And so we usually just make the conclusion that Q equals CIA and CFS, we might as well just use the easy way and not bother converting the inches per hour into feet per second, not bother converting the acres into square feet. It's just one of those rare victories that the traditional unit system will give you when the units work out in a reasonable way. So we'll take it. All right. So any questions about that illustration? Well, let's talk about rainfall then. Where does it come from? Precipitation begins with the movement of air. And I guess in theory you could say, take it a step back further, and it begins with sunshine evaporating moisture. So it begins with both. It begins with sun evaporating water, and then the air that water is in has to move around before it can rain. Okay, now the movement of air depends on temperature differences at different elevations in the atmosphere. It depends on pressure differences as two fronts come together. Air movement globally depends on the rotation of the Earth. Now the first kind of broad factor that causes air movement across the globe is called Hadley circulation. And the way to understand that is that we kind of instinctively know it's warmer at the equator. Why is it warmer at the equator? Is it because it's closer to the sun?
Roughly speaking, yeah. In the conjunction of location, yeah.
That's not the dominant factor. It's infinitesimally closer to the sun. If you think about how far away the sun is, and it's a little bit closer to the sun compared to the poles, but that's not really the driving factor. It's warmer at the equator because the sun is shining directly on the equator, and it's shining at an angle at the poles. Like if you think about the solar rays are coming in this way, and they directly impact the Earth here, whereas they just come at an angle, and the atmosphere is reflecting a lot of the solar radiation at the poles. So it's more about the impact angle of those photons coming from the sun. So we all know it's warmer at the equator, and warm air rises. Warm air rises. All right. So in this figure, it's showing the warm air is rising, and cold air will fall. And so we've got this place, the equator, where the warm air is rising, and two places at the poles where it's cold, and so the air is going to be falling at the poles. And so it kind of sets up this conveyor belt. It's illustrated really well here, where you've got the rising and then the falling, and so the rising is pushing the air across the top, the falling is drawing it down across the bottom. And so the first general trend in Hadley circulation is that in the northern hemisphere, the air movement, the general motion, is towards the south. In the southern hemisphere, the general motion is that the air is going towards the equator. And so the air is always converging on the equator because of those temperature differences. Okay, so you're with me so far, right? The next general trend is the fact that while this is happening, while the Hadley circulation is happening, the Earth is also rotating. And the air has viscosity, and so it kind of smears as, those pockets of air, as the rotation occurs, they're getting twisted. As the belt is also going, the globe is moving, and it's kind of dragging the lower layer that's close to the Earth's surface. It's dragging it in the direction of the pole's rotation, and the stuff up top isn't getting dragged in the same way. And so it sets up these smaller pockets having to do with, this illustration kind of shows that as something is rotating and the direction is southward, it doesn't take a straight path relative to the Earth's surface. It's just kind of an analogy, this little animation. So the main thing you need to take from that is that the Coriolis force is setting up these pockets where the lateral movement of the wind occurs. And here in North America, we just kind of take it for granted that weather comes from the west and goes towards the east. But that's not true everywhere on the globe. Like if you want to know what the weather's going to be, you look at Kentucky and Ohio, right? That'll give you some insights into what the weather's going to be later today or tomorrow. You look to the west. But in other places, like in South America, they would look to the east because the trade winds have a direction from the east towards the west, which is different from the westerlies, which prevail at our latitudes. And so it's important to have an understanding of like what direction the wind is coming from and the weather is coming from. The air movement over obstacles is going to affect how much precipitation occurs and where it occurs. And so, why is there a desert in a certain place? And why is there a tropical rainforest in another? There may be in one spot a forest, like a tropical rainforest, and another spot a desert, but they're at the same latitude on the Earth. The Sahara Desert and the Amazon jungle. And those two latitudes overlap, but a lot of why you have a desert in one spot and a jungle in another may have to do with the direction of the wind at that location. And so the jungle is going to be downwind of an ocean where there's a lot of moisture being lifted up out of the ocean and then deposited into the jungle, whereas the desert is going to be downwind of land that's already dry, and it gets drier as the sun heats it and continues to blow it towards the west. So like the Gobi Desert or the Sahara Desert, they are in the latitudes of these trade winds, and they're to the west of other stretches of land that are moist, but all of the rain that was going to fall has fallen, and there are no more factors that would force the precipitation. Okay, so precipitation begins with air movement. Here's just a couple of illustrations from the textbook that shows how widely dispersed rainfall can be. And what they did is they tried to identify for certain water molecules where the rain fell and where the evaporation occurred. And it just shows that there is a lot of movement through the atmosphere. And this is kind of speaks to why air pollution in one location can affect another spot, where a coal power plant in Ohio can cause acid rain in Canada, or why air pollution in Poland can cause acid rain in Sweden. And this is just showing, for instance, here in South America, that there was evaporation occurring in the Amazon, but that water, when they radio labeled it and measured where it was found, kind of was dispersed over the entire South American continent. That's just showing the power of air movement across the globe. So here's the basic procedure for how rain forms. First of all, moist air has to be cooled. So air has, you know that air is mostly nitrogen, right? That's not big news. It's mostly nitrogen, then there's a lot of oxygen, some carbon dioxide, there are noble gases like helium, xenon, there's hydrogen, but there's also, in all air, there's some moisture that has evaporated. There's water in the air, and you hear about it when they say what was the humidity today, and you probably during the summer have heard about the heat index, where the heat index is kind of taking into account how hot it feels based on not only how hot it is, but then also the humidity. Why does it feel more hot when it's humid out? Why does it feel more uncomfortable and more hot? Like, how does your body cool itself? Through sweating. If it's humid out, then your sweating isn't doing much because your sweat isn't evaporating, it's just dripping off of you. Ideally, like when you're out in Utah or Arizona or something, on a hot day there's no puddle under you because the moisture evaporates from your skin and it cools your skin as it evaporates. The phase change uses energy. So there is moisture in the air. We know of it as humidity, and as the air cools, what that does is it increases the humidity of the air as it cools, because different fluids can hold, like the solubility of water in air decreases as the temperature goes down. Maybe you did an experiment in science project in high school. Like, do you remember trying to dissolve salt in hot water versus in cold water? What's the trend that you know from that, Austin?
In the hot water dissolves more.
That's right. Yeah, hot water will dissolve more salt and more quickly. And so what you can take from that is that the solubility of salt in water increases as the water is hotter. Okay, so in air, if the air is cool, it can't hold as much water. Warm air can hold a lot of water. And so the first thing that causes rain is when air, which also has moisture, starts to cool. And when that air is cooling, what happens is the relative humidity is increasing. And so how saturated it is with moisture is increasing as the air cools. So it's kind of like you're getting closer and closer to the limit of how much moisture can be in that air. You can't put 100 gallons of water into the air in this room, for example. Just the air can only absorb so much. But how much water the air can handle varies with temperature. So precipitation first begins with cooling of air. And as the air cools, it's bringing the moisture content closer to saturation, to that limit of how much it can handle. Now, cooling of air sometimes happens when the air is moving laterally, like side to side. Sometimes the air is cooling off when two fronts come together. But the most significant cooling occurs when a pocket of air is lifted in the atmosphere. And the reason for that is it's really cold up there. If you've ever been on a plane and the pilot told you what was the temperature outside, or maybe you saw it on the readout on the side of the plane, it's really, really cold in the upper atmosphere, like -60 Fahrenheit, -100 Fahrenheit. It's freezing up there. And so as air rises, it cools off. And so here, where it says the hydrologically significant precipitation, the rain that really matters, you know, that's going to cause flooding, that's because some moist air cooled off through being lifted up. Something forced that moist air upward. So that's the first phase, is that the air is cooling. Now as the air cools, the moisture starts to aggregate on a nuclei. It may be dust or salt particles or even pollution, but there's some sort of like a spot that the air has to start depositing its extra moisture onto. It's the site that the precipitation is growing on. And so it's kind of a process where A fog may have a really small diameter. The diameter of the moisture particle may be 10 microns to 100 microns, but as the air is cooling and the air has to get rid of the moisture that is dissolved as a gas, you know, the H2O is a gas, but then it's turning into liquid H2O and it has to go somewhere. So it goes from the vapor phase into the liquid phase on these nucleation sites, and then when there's a particle up in the atmosphere, like you can actually visually see it, a cloud, then any extra moisture is going to continue to go onto that cloud, and the particle continues to get larger and larger until no longer can it be supported in the air. Now it's going to start falling downward. You know, just the general movement of molecules can suspend a particle up to a certain weight, but then the suspension of the atmosphere can't hold it any longer, and so in a thunderstorm, the droplet diameter may be even larger than a millimeter in diameter, big fat raindrops. All right, the droplets continue to grow not only from the moisture going from the vapor phase into the liquid phase on that site, but also as the droplets collide with each other. Then the particles can grow that way. If there's wind driving it around, or if the particle is falling downward, so a raindrop, a small raindrop, finally has enough weight to it that it's going to start overcoming the suspending effects of the atmosphere that it's in, and it's falling downward. It'll fall slowly at first, but it's falling through a cloud. It's falling through a localized spot of oversaturated air that's oversaturated with moisture, and so it's going to be falling into other raindrops, and those raindrops combine and they progressively get larger diameters, and then this process continues until the raindrop hits the ground. And occasionally a raindrop may fall through the atmosphere and it may evaporate even before it gets to the bottom of the ground. That's kind of ironic that, you know, as it falls down, it's now getting into warmer air that isn't fully saturated. So the droplet was growing up above, but then the droplet may be shrinking as it's falling down towards the surface. So here's a diagram that shows something called the adiabatic effect. The adiabatic effect is air in the upper atmosphere is cool because there's less pressure there. It's kind of a all these factors are happening at the same time. You remember that in fluid mechanics, if we have a tank of water and we go down through the fluid, then here's location 1, here's location 2. The pressure increases as you go down through a fluid, right? For water, it's 9810 newtons per meter cubed. So for every meter you go down through water, pressure increases by 9810 pascals for every meter of depth. Well, air also has a unit weight. This is the water unit weight. The unit weight for air, I think, is about like 12 newtons per meter cubed. So the atmosphere is a fluid, and the pressure of the atmosphere is lower at the high elevations, and the pressure is high down below. That's why when you fly in a plane, they have to pressurize the cockpit. Well, and the passenger area too. The cabin, thank you. They pressurize the whole plane because you wouldn't be able to breathe up there, because we need enough oxygen to survive. So up above, there's very little pressure, and so what that means is that it's cool up there as well. Has anybody here ever refilled the Freon in your car? Or maybe, you know, the canned air, like to spray dust off of a keyboard? So if you spray that, what happens to the can? It gets cold. That's because a gas that's expanding cools off. That's what's happening here. As you go up through the atmosphere, the pressure is low, so a certain volume of water would occupy, a certain volume of air occupies more space. So it's expanding, and a certain, like if we had just a unit, a certain volume of air that's full of moisture, if because of various factors causes this parcel of air to be lifted up through the atmosphere. It's expanding, cooling. As it cools, the solubility of moisture decreases, and that's kind of what pushes it towards precipitation. Is it can't hold as much moisture as it did when it was down below. So the sentence that I've written here I think is really important, and it may not be this way in your notes. I may have made some edits here, so I'd suggest you write this down. At some point I'm going to ask you to regurgitate this on an exam, or better yet, understand it and write it in your own words. But I mean, if you wrote what I had written, you'd get credit there. But this is saying the air is rising, the pressure decreases, so the volume expands. That causes the air to cool, and then when the air gets colder, the relative humidity increases until saturation occurs, and then the water's got to go somewhere. It can't be dissolved anymore, so it's got to go onto those nucleation sites and start forming rain. Have you heard the old saying, you don't have to go home, but you can't stay here? So the moisture can't stay dissolved in the air anymore, so it's got to go somewhere else. And so the moisture starts to go into the liquid phase on these nucleation sites, onto the dust. So this is the adiabatic effect. When air is lifted, it's probably going to rain, because the air can't hold as much moisture up high as it can down low because of the cooling effect. I can't emphasize how important this is. It's so important. I mean, it's obvious to me because I've been talking about it for 15 years now and learning about it before then, but I'm always shocked when this doesn't sink in for students and when they're not able to explain the adiabatic effect on a quiz or an exam. It's kind of the foundation of everything. All right. So what causes air to go up? So I told you rain is caused by when air goes up. Lifting. And so what causes lifting? The three major causes that we're going to discuss today are convergence, orography, and convection. And these are important keywords. We haven't had a quiz yet where you had to define just one of those terms on the list, but we're having a quiz on Friday, aren't we? So it's going to have a StormCAD problem. I already told you that. But it may not only be a StormCAD problem. All right. I see some knowing smiles. All right, so let's talk about convergence. Convergence is when a low pressure system and a high pressure system come together. Now keep in mind the adiabatic lapse rate. The lapse rate is talking about how much the temperature changes as you go up through the atmosphere. And if the atmosphere is dry, then it would change 9.8 Celsius degrees for every kilometer of elevation. And by the way, the size of a Celsius degree is the same as a Kelvin degree. So sometimes you'll see this adiabatic lapse rate expressed. Maybe they'd say like 1 Kelvin per 100 meters. That's essentially the same thing as 9.8 Celsius per kilometer. So every meter of elevation, if the air is dry, the temperature would decrease 1 degree. If the air is fully saturated with moisture, it doesn't change as much. So, you know, exactly how much the temperature is changing partly depends on how saturated with water the air is. This is a top view. Back in the old days when they'd show the weather on TV, like in the 50s or the 60s, they'd have these lame weather maps that weren't animated. They didn't have like cartoon smiley faces and stuff. They were diagrams like this, and they'd show your city, and they'd kind of try and illustrate where the air was cold, where the air is warm, because one of the things that can cause a storm is when colder air is mixing with warm air. And the reason why is that there are density differences between warm air and cold air. Knowing what you do about fluids, what would you expect has a greater density? Warm air or cold air? Like, what is more dense? The cold air, that's right. You know, warm air has expanded, so it's less dense than the cold air, which contracts. And so what happens when a windy, cold air is converging on warm air. Now this is the side view of the same area that we were looking at. This is the side view at AB. So we're looking at it from the side. So you have a cold front that's blowing in towards an area that used to be warm. What can happen is the warm air rises really quickly as it's being forced out of the way by the approaching cold front. And so that warm air has been lifted by the approaching cold front, and it can cause a thunderstorm. And you've probably noticed that before, that sometimes the temperature changes suddenly right before it rains. Like I go trail running and I check the temperature before I go trail running. It maybe will be 60 degrees and I'm just wearing a t-shirt, and I go out and then it starts raining and I get back and look on the thermometer. Sometimes now it's 48. It went down 12 degrees just in the hour I was out, because it was a cold front that was approaching, and so it's simultaneously getting windy, cold, and that's what forces the rain, is the warm, moist air was lifting abruptly. Now that's a thunderstorm. Lots of rain, hydrologically significant. Less significant, like a light rain, is caused when the warm air is rising gradually rather than suddenly. And so where the warm air is being pushed towards a cold front, it's going to rise very slowly over the cold front. If it's the encroaching front, the warm air is encroaching slowly over the cool. And of course they do mix. It's not like they stay separate forever. There is diffusion between the two layers, and eventually they're going to mix up and be the same temperature. But it's just when the two fronts come together. And so that's convergence. It's called frontal lifting. And you can read more about it in your book. The thing to keep in mind is that the abrupt, hydrologically significant precipitation occurs as the cold front encroaches on the warm. And it's the light, long duration precipitation that is just kind of a mist, a day-long drizzle. That's caused by it was already cold and now the warm air is coming towards you. So you can kind of tell, like in the forecast, if they say it's going to be rainy today, you can tell if it's going to be a lot of rain, intense rain, or if it's going to be just a drizzle. Is it today warm and it's getting colder, or is it cold now and it's getting warmer? And how the temperature is changing can be a clue as to the intensity of rain that you expect to see, because that temperature change is going to tell you about how quickly the air is rising. All right, this is an island. This is a picture of an island. And here's a peninsula that's sticking out on the island. And part of the island is green, and part of the island is very dry. And it's not because there's been a defoliant, there wasn't a forest fire. This just permanently not as rainy on one side of the island as it is on the other. They call the windward side is the name of the part of the island that is really moist, because that's where the water coming off, the air coming off of the ocean, which is nice and saturated with vapor, is going to be lifted because of some factor, but then it's dry on the other side. And that effect of orography is that when there's a physical barrier like a mountain, that the wind has to blow over the mountain, because of the physical obstacle, it's going to cause precipitation on one side, but then as the air goes back down again, it's warming up. So the precipitation occurs when it's cooling. So the air was getting cooler on this side of the mountain because it's in the process of being lifted up. But then as the air goes back down again, it's warming up, and there's no driving force getting the saturated moisture out of the air. Here's a short video that I found that illustrates this cloud over a time lapse in Wyoming. What he's saying is that the moist air is lifted as it's forced over the mountain, and then as it goes down the other side, the pressure is decreasing, it's contracting, it's warming up, So that vapor that you saw, it's almost as though it's magically disappearing, but it's not disappearing. It's going from droplets and it's going back into the vapor phase. So it's H2O. Instead of being H2O liquid, what we're seeing here in the cloud is a very small particle of H2O liquid. On the downside of the mountain, it's going back into invisible water vapor. Any questions about that? All right, here is the island of Oahu. And I've only been to Oahu one time. And you want to stay on the windward side because it's nice and green and tropical. And there are a couple of nice beaches over here on the leeward side, but it is dry and brown, and it's kind of the lower income part of the island is over here where there is less rainfall per year. And the really expensive, like, nice houses are over here, Kailua. So the effect that you see here, you can kind of tell from the shading that the mountains are here, and so the rainfall is coinciding with the mountains, and then the flat the flat parts of the island are where it's not raining as much because there isn't any lifting that occurs. So orography is the second effect. So the first one was convergence or frontal lifting. The second one is orography, which you can think of as an obstacle that's forcing the air up to cool, to oversaturate. Convective lifting is where the air is being lifted up due to convection, which means radiation from the sun heats up the surface during the day, and then in the afternoon, when the surface is nice and warm, it's lifting the air up. And you've probably seen that gliders can fly around almost indefinitely in the afternoon because of the thermals, as they're called. It's the air that's rising because it's been heated at the Earth's surface. And so if the ground is really warm, then it's emitting that heat. It rises the air, it heats the air that's close to the surface of the ground, and then that warm air rises up. And you sometimes during the summer can see they almost look like mushroom clouds, especially like in the plains. I used to live in Kansas, and it almost looked like a nuclear bomb had been dropped over there, but I mean, it's not a nuclear bomb. It's just that there was, for whatever reason, a lot of sun on the surface over there earlier in the day. Maybe it wasn't cloudy, or maybe it was there's something about the land there. Maybe it's like a big field that's brown. And, you know, of course, different temperatures can attract heat in different ways. And so like a recently tilled field may warm up faster. And so then there's more lifting there. And this is responsible for the effect of the afternoon thunderstorm. And sometimes if you're ever flying in the summer, it's interesting, there's a much greater chance of delay if you have like a 5 p.m. flight going through Chicago than if you have a 7 a.m. flight going through Chicago. Because by 5 p.m. there's been enough convective lifting in the flat area in the Midwest that there's probably going to be some storms rolling through, and it may be that they're large enough to cause flight delays. But in the morning there hasn't been any heating yet, and so there hasn't been any lifting, and so convective lifting is associated with that afternoon thunderstorm effect. And so, you know, some of the air that's being heated is also moist, and then as it goes up it cools, oversaturates, and causes precipitation. So this figure is just showing the adiabatic effect, that the temperature of the air is cooling as it rises, and eventually there's a crossover point. Here the S refers to saturation, and it's the point at which the relative humidity is 100%, that the air can't hold any more moisture, and if it cools further, then that moisture has to go out of the vapor phase and into the liquid phase. So all of the precipitation types that you can think of, whether it's snow, hail, sleet, or rainfall, they all rely on the droplet growth, the effect of moisture accumulating and agglomerating onto some sort of an initial nuclei. And one of the interesting things about those particles that are up in the air is that very small particles typically will have a negative charge. And this is maybe something that you've learned about in environmental engineering, or if you haven't yet, you will soon. That even in water, small particles like clay particles that are suspended in the Ohio River have this negative charge and they repel each other, and so that repulsive effect has to be overcome with like a coagulant in the case of water, or in the case of the atmosphere, those nuclei stay suspended because of the repulsive charge, but then once the water starts to form on them, then that reduces the negative charge and allows the impact and aggregation so that the precipitation can form. Let's see, how much further will we go today? We've got a few minutes. We'll talk about precipitation gauges in detail on Friday, but since we've got the time, let's go a bit further. This is a map that comes from a government website that shows all of the places that precipitation is measured in the area. So we have Charleston over here, Huntington, so it's kind of that residential corridor between the two. And the good place to get precipitation data is at an airport. That's where you're going to have the most reliable measurement of precipitation for obvious reasons. The weather is really important in the aviation industry. And at an airport, the records having to do with precipitation, I think at Huntington Airport, go back into the 60s. At the Charleston Airport, it may go back even further than that. But then there are a lot of gauging sites that are shown on the map here where they're not getting the same kind of data. At the Huntington or Charleston Airport, they're measuring how much precipitation there is in 15-minute increments. And so they know every 15 minutes through the day whether there was any precipitation. There are other gauges where it may not be an automated gauge, it may be just a volunteer who goes into their backyard and looks in a physical gauge that looks like a graduated cylinder, you know, how much extra water is in their graduated cylinder today based on the last 24 hours of precipitation. So depending on the site, some sites may go back only 10 or 15 years, and in some cases we can find locations where there was maybe 20 or 30 years worth of precipitation data when they had a volunteer at a site, but now they're not gathering the precipitation data at that site anymore. And so sometimes what we have to do is we have to use precipitation data at locations that surround an area of interest and then make interpolations or estimate how much rain there would have been in this spot in between based on triangulating how much rain we saw in Barbersville, West Hamlin, and Hurricane, and then kind of just interpolate in between. Across the country, nationwide, this logarithmic scale shows how much rainfall data we have and the number of sites that have the length of the records. And so, for instance, it's showing that we've got about 1,000 rain gauges nationwide with 30 years of precipitation data. If you wanted to look back 70 years, then there's probably about 600 rain gauges across the country that have 70 years of precipitation data. But there is only 8 sites where we have more than 140 years of rainfall data. And the reason why that's important is that oftentimes the storms that we're interested in for design purposes are only going to come through very rarely. For instance, if you're designing a dam, you don't want the dam to fail during the 10-year storm. You don't want it to fill up and overtop in the 100-year storm. I mean, ideally for a dam, what they're designing for is maybe the 10,000-year storm or the 100,000-year storm. They're really planning on the worst case scenario and they want it to hold up no matter what. Not every structure has to be built to that same standard. Interstates, for example, interstate highways are typically, they have their drainage systems sized to handle, they're supposed to, the 100-year storm. so that during the 100-year storm there isn't going to be water getting onto the roadway. And so the problem is let's say you want to put a new interstate through Waterloo. I guess that's probably in, I don't know if that's West Virginia. Yeah, it's West Virginia. I don't know, that's Ohio. All right, yeah, it's Ohio. So let's say that we're going to put a new interstate highway that runs through Waterloo, and we want to know, what does the 100-year storm look like? Well, to really know what the 100-year storm looks like, you'd need 100 years of storm data, and you may not have it. And so there are ways that we can extrapolate, maybe if we have information on what the 50-year storm looks like. And so if you had 50 years of storm data here, but then there's another spot where you can say, well, the 100-year storm is 20% larger than the 50-year storm. And that seems to be a reproducible trend in places that have the same kind of topography as Waterloo. Then we can extrapolate. So there's really a lot of statistical regression and extrapolation that happens when we're trying to create intensity, duration, frequency curves that are originally, they're based on real measurements of rainfall, but the problem is that America is such a big country and we have so few rain gauges that go back very far that you have to do a lot of guesswork to come up with the storm size that you're going to use to size a lot of the storm drains and culverts and drainage ditches and so on. So we'll actually download some real rainfall data, and when we do, one of the ways that it can be expressed is with what's called a rainfall hyetograph. Most commonly, rainfall hyetographs are expressed as the intensity of a storm over time. And so in this case, what you can see is that every hour of a storm, they've measured the rainfall in terms of what was the intensity, how many inches per hour was there in each 1 hour period. And so the area under the curve is going to be the depth of the storm. If you multiply the intensity by the duration, then we know that in the first hour about 1.05 inches of rainfall fell. Then in the second hour, about the same amount of rainfall happened. So a rainfall hyetograph is different from a hydrograph. Last class period I drew a hydrograph on the screen, and you've done that for your homework. Remember the hydrograph that you prepared for the pond sizing? You had the flow into the pond and the flow out of the pond that you represented graphically. In that case, the vertical axis was flow, cubic feet per second. It was the runoff, whereas this is just the depth per time. So it's how much rain is coming out of the sky over time. You can also express the rainfall as a cumulative total during a storm. And so what this is showing is that, for instance, during January 8th's storm event, the rain started at time 0. If this is the cumulative rainfall amount, it totaled almost 5 inches, and so it's a huge storm. This, where this line is the steepest, would be when it was raining the most intensely. And so the slope of it is a big increase of rainfall depth in a short period of time. Whereas, for example, this June 23rd storm, it's raining much more slowly. The depth isn't as much, but also because this is relatively flat and it's only increasing gradually, it means that that was probably one of those storms where it's just a warm front encroaching on a cold front, and it's the slow all-day drizzle rather than a big hydrologically significant thunderstorm. So these are two different ways that you could graphically represent precipitation amounts. Okay, so just to reiterate, we're going to have a quiz in class on Friday, and you're going to have an HY8 problem, and you're also going to have some sort of a concept question where I ask you to define a term or explain a concept. So we'll do that at the beginning of class on Friday, and then we'll continue talking about precipitation.